let's quickly recap what we did in the last class. We said that we have completed looking at first order differential equations in some sense. Then we started looking at second order differential equations. And the basic template that one can look at is d2y dt square plus a1 dy dt plus a naught y equal to some right hand side b naught. And there are several ways in which one can look at solutions. Laplace transform is one of the methodologies that we saw. And we said there's nothing more to do as far as using of the Laplace transform is concerned, because we have already gotten the framework in place. So we started looking at a couple of examples. And the first example we saw was that there's a right hand side which is the Dirac delta function. And you can take the Laplace transform and do the algebra, and you come up with the Laplace transform equal to something. And you can invert it and you get the solution. Okay? And I had also shown you that one of the softwares that are available, you can directly put the governing equation, put the Dirac delta on the right hand side, and you'll get the same solution. Okay? So that's something you can do. And the only point that I wanted to show you or draw your attention to was the fact that when you have such situations, the so-called initial condition, even though we have put x dot 0 as equal to 0, when you look at the solution, you get x dot 0 equal to 1, and that comes about because of the fact that you're putting a impulse function at t equal to 0. Okay, so that kind of a discontinuity is going to be there. But that also gave you a physical feel of what is going on, and one can think about the fact that the right hand side, which is a delta function, this second order differential equation represents some physical system, as we will see later on today. But if that's a physical system, giving it a forcing of a delta is something that's a little bit uncomfortable from a physics point of view. So what is more comfortable is from the solution what you get, which is the boundary or the initial condition being equal to some specified number, which is much more comprehensible than saying that there is a right hand side. So I don't know what it is, it goes up to infinity and then the integral equal to 1. Okay. But the mathematicians have given us both these options, so you can look at it in a physical manner also in some sense. Then we looked at another example, and this is where once again the Laplace transform has been used, and it's much more messy or messier than the earlier example, and you can go through all this algebra and get the solution, that kind of longish messy looking solution. Or you can just go ahead and use one of those nice online tools available, and you will get that solution. Okay. Another way of looking at it is the same example we have solved by using the delta function on the right hand side, and the solution is nothing but that y star that we talked about, and therefore you can go ahead and get the solution as the convolution integral of the y star, which is what's shown in the brackets there, and the right hand side which is there. The integration itself is a fairly messy integration. You can go ahead and do it, or I have used one of these online tools to get the integration, and you should get the same solution whatever we had earlier on. So then we said that if the solution is discontinuous, you can go ahead and use the Heaviside function. And if you are using something from the first principles, then the integration is a little bit more messier than what the earlier integrals are. Okay, thank you. Okay. All right. So you can, if you were to go ahead and look at the integration on your own, this is a relationship that is helpful to you. And because the Laplace transform of the Heaviside function, because the right hand side can start anywhere, and in here it is starting at C, and the Laplace transform of the Heaviside t minus C, ft minus C, is easily found out as compared to f of t. And this was an example we again looked at, and just basically do a decent amount of algebra to go ahead and get to the final solution. All of these are fine. And then one last thing we did was look at the integro differential equation, and we used again the Laplace transform as the vehicle to go ahead and get the solution. In the past, we have said that the Laplace inverse of the product of two functions in the Laplace domain are going to be equal to the convolution of the functions or the corresponding functions in the time domain. And using that definition, we have not proved it, using that definition, you can go ahead and get the Laplace transform of an integral as being the Laplace transform of the function itself divided by s. And once you do that, the integral differential equation once again becomes an algebraic equation which you can easily solve. And we did this again. And you can go ahead and look at the details, but I have used one of these available software to get the solution. Okay. All right, so that was where we were when we quit last time. You have now a home assignment has been uploaded, and you are supposed to be submitting it, I think sometime this Thursday or something. And somebody asked me at the end, what is the submission? So in the home assignment, something is written which says you need to submit only question number whatever, some 1, 2, 5, 6 or something. You are expected to submit only those questions. Okay. And there are a whole bunch of other questions which you can go ahead and work out on your own. And also these questions you can go ahead and solve either by going ahead and actually taking the Laplace transform and then taking the inverse, or directly going ahead and using a software. I'm okay with either of these as far as the home assignment is concerned, and the assignment is to be uploaded on Moodle, and there is a hard deadline, whatever that deadline is, I don't remember. After that, Moodle is not going to accept any submissions. Okay. And each assignment has got a very small grade associated with it, so don't bother if you are not able to submit on time. There are n number of other assignments which you can go ahead and work out and compensate. All right. Now the other thing is that the assignments which are given to you are kind of representative, and they are on the slightly more easy side, in the sense that that's more like a practice for you. the exam is going to be slightly more difficultish, in the sense that on the exam we would like for you to display an understanding of the class material as well as what is available as assignment questions. Okay. All right. So we said that we are going to leave the Laplace transform business now, at least temporarily, and look at some other methodology which is going to be useful for solving situations of this nature. And given a particular situation, you are welcome to use whichever is going to be more convenient to you. Okay, so there is nothing hard and fast about use this or use this, but you have a couple of different methodologies under your belt so that you can use whichever you are more comfortable with. Okay. All right, so we said that we would start with a differential equation, a second order differential equation. You have got d2y dt square plus a1 dy dt plus a naught is equal to some input function bi. Okay. So this is the differential equation, second order equation that we are going to be starting with. And if you recall one of the earlier classes, we have said that if you have a linear equation, then the solution is going to be equal to the solution of the homogeneous part, which is the solution by putting the right hand side equal to 0, and the addition of the solution to the homogeneous part plus some kind of a particular integral, which is going to be the solution or a solution with the right hand side in place. Okay. So first we are going to look at the homogeneous part and see solutions to the homogeneous part, and then we are going to go ahead and talk about the particular integral. Okay. So this guy is a second order equation, and what we say is that we are going to get the solution by hypothesizing that y is going to be c e to the power of some rt. Okay. So y is c e to the rt, and if you go ahead and plug this in here, y double prime is going to be, or y prime is c r e to the rt, and y double prime is going to be c r square e to the power rt, and y of course is whatever is there, so let's just plug this guy in. So you have got c r square e to the rt plus a1 c r e to the rt plus a naught y, there is a y in here, plus a naught y, which is c e to the rt equal to 0, and e to the power rt is not equal to 0, so you can go ahead and divide through by this guy, and what you end up with is a standard quadratic equation, a1r plus a naught equal to 0. So we are hypothesizing that there is a solution to this differential equation which can be obtained by saying that y is e to the rt, and if you do the algebra you come up with some kind of a quadratic equation, and the solution for this is known to us from algebra, a square minus 4a naught by twice. Okay. So this is the solution to the algebraic equation. Okay. Now if I now am looking for r, this is a quadratic equation, so I'm going to get two roots of this, so my solution is y c e to the r1t plus c2 e to the rt. So this is my solution to that homogeneous equation. All right, now this is fine, as far as if we are saying that I have a situation of this nature and my roots are real, then I am going to be getting the solution. Even if the roots are imaginary, I am going to get a solution. But if I look at this governing equation, this is where we had jumped a little bit last class. This second order equation physically represents a spring mass damper system. If you don't understand what is a spring mass damper system, it's perfectly fine, nothing wrong with that. So there is a mass that is attached to a spring and a damping unit, and then this guy is given some kind of forcing. And if you go ahead and from your mechanics course, you will see that the free body diagram, there is going to be a force, there is going to be an inertia, there is going to be a damping, and there is going to be a spring force. So these are going to be balancing each other, and you get your governing equation as mx double dot plus cx dot plus kx is some right hand side, which is going to be f. Okay. Now, getting this equation is not important. All that I am trying to emphasize is the fact that this is a physical system that can be modeled like this. Okay. And if you do a little bit more algebra, we can put it in the form in which we had our original equation, which is QO is KQI. And if you recall, we had said that our first order system we had said was something like that. Okay, so this was a first order system, and we said that if you've got a temperature sensor, then physically that's how this guy is modeled. And now we are saying that if you have got a spring mass system, this is the equation that governs it. So there is some physical meaning to these equations. They are not just mathematical abstractions. That's all I want to show you when I'm showing you this, nothing else. Okay. If you don't know how to get that equation, it's perfectly fine. Nothing wrong with that. Okay. Now, the reason I'm bringing this is we just made a statement that we have a second order system, and we are now saying that the solution is going to be C e to the power of RT. And if you have got real solutions, you are decently happy with the solution that you have. And if I go ahead and solve this guy, you are going to get something like that, which is just the same quadratic that we had. But what you see there is under root of some zeta square minus 1. There is some physical meaning to this zeta. We don't want to get into that. But what I'm trying to just tell you is that the zeta square can be less than 1, it can be equal to 1, it can be greater than 1. Okay? In which case, what you see is that you can end up with roots of this equation, which is R1 and R2, R1 and R2. So these guys can be real, they can be imaginary, or they can be equal to each other. Okay? So that's coming directly from this equation that we have. Alright, so real roots I'm okay with. Imaginary roots, when I say, and then I say that there is a physical system, then I'm a little bit uncomfortable saying that the roots of the so-called governing equation are coming to be imaginary. Okay. So I would like to somehow use the tools that I have to convert that imaginary number into some kind of a tangible real number. Okay. So that's what all this business is all about. Okay. All right. So let me just say that the roots came out to be R is equal to M plus minus IN. So the two roots are going to be complex conjugates. Okay. So one of the roots is going to be M plus IN, the other root is going to be m minus in. So that's what comes out from here, and the solution y is going to be c e to the power of rt. Okay, t or x, that does not matter, and somebody pointed out that there is a small issue with the home assignment. There was some boundary condition which was not properly given, but it's fairly easy to figure out that that was an error. Okay, so whatever it is, this is the independent variable which is governing the system. Okay, all right. Now what we say is, I am not liking an imaginary solution to my physical system which is there. So can we somehow modify this guy with the tools that we already have to get a solution which appears like a real solution? Okay. So that's what the agenda is. So what we say is e to the power of I mx, for example, I nt. We can use the Euler identity and say that this is cos nt plus I sin nt. Okay. So this again we know from our high school math. So e to the power of int is cos nt plus I sin nt. And now what we say is, we have got these two roots, e to the power of m plus int, e to the power of m minus int. So what we say is, let me say that the solution is now a linear combination. Okay, I'm not going to take the roots that are coming out the way they are coming out. Let me just say that I'm going to consider a linear combination. So I've got e to the power of mt, m plus int. This is going to be e to the power of mt times e to the power of int, which I'm going to now put it as cos nt plus I sin nt. Okay. So this is one of the roots, and what we say is that, let me say e to the power of m minus int. This is e to the mt cos nt minus I sin nt. Okay. So even though I have got these two as the roots of the equation, I'm going to consider the solution as being the sum of these roots. Okay, nothing wrong with that, right? We have said that you have got a linear e to the power of r1t plus e to the power of r2t is also a solution to the governing equation, right? So that's what our first, in our first class we said that a linear combination of the solutions is also a solution. So I'm going to do this. Okay, and if you do that, okay, now what happens when I sum these two guys up? When I sum these two guys up, this guy goes away, this guy goes away, right? The summation is also a solution. So I'm not going to say that e to the power of IRT is a solution, but e to the power of IT plus this other root, that I'm going to take it as a root of the equation. Okay. Which means that I now have gotten rid of this I guy here. Okay. So I've got the solution, one of the solutions at least. So e to the RT. So when we add up these two guys, we get y is going to be e to the power of mt cos nt times, let us say, some c1. Okay, that's one of my roots. Okay. Now I have successfully eliminated that I guy in there. So how to eliminate the other guy? So what would be my second solution therefore? The difference of the two, right? The sum of the two got rid of the I. The difference of the two is going to keep the I, but then what will I do therefore? The I still remains, right? When you take the difference, we will absorb it in the constant. Yeah. Because any constant is fine, so I'm going to absorb it into the constant. So what we are saying now is that this is one of the roots and the other guy is going to be e to the power of mt cos nt plus I sin nt e to the power mt cos nt minus I sin nt. I'm going to subtract these two guys now. So when I subtract these two guys, this is going to go away and I'm going to say that I'm going to multiply through 1 by I, which is perfectly fine to do, right? And so therefore my other solution becomes this. This is y1, this is e to the power of mt sine of nt times c2. That's my second solution. So instead of having e to the power of a plus ib, where this I guy is sitting, which is I'm uncomfortable because it is the solution to a real system, you have mathematically been able to do a modification or a manipulation because it's a linear equation. Because it's a linear equation, we have already shown that a linear combination is a solution, and therefore if I have got complex roots, I still get a nice enough solution which looks like e to the mt c1 cos nt plus c2 sin nt. This is one way of writing the solution. It's perfectly fine for you to say e to the power m plus int plus m minus int. That's not wrong. Okay, but this is a desirable way of getting the solution to that if my roots are complex. Okay.
So, if we were equally comfortable in absorbing the iota term to the constant, why didn't we did that even when we got the solution in the form of iota only? Because it will be e to the power some iota. So
you can do that. You can do that. You can do that. But e to the power of I will stay there, right? Where will I absorb it? Right? I have got c e to the power of something, right? So e to the power something stayed there, right?
Yeah.
Right. So e to the power I something we said was cos plus some I sine.
So,
right?
Since I is also
So if you want, you can add up those two and then say that my I terms and then the sine terms and then the cosine terms, that is also fine. That's basically what we have done. Okay, basically same thing as what we have done. Okay, anything else? Okay, so this is the standard solution if your roots are going to be imaginary. Okay. All right, so now the next thing we say is what happens when the roots are equal. Okay, so the solution when your roots are going to be imaginary is if your root is of the form m plus in, you can go ahead and write it in this particular form. Okay, they are complex conjugates. You're going to have m plus in, m minus in, and the cosines and sines are going to be showing up. Okay, so if the roots are repeated, okay, so it's also possible that the roots are repeated. That is, if this guy a square minus 4a0 equal to 0, which is a finite possibility, in which case you are going to get only one root. Okay, so your root is going to be just simply 1r is going to come, and the solution is simply e to the power of r1t, and you need one more solution, right? You need one more solution, and these mathematicians are very clever, so they came up with a solution. And what they said was that I'm going to now hypothesize. I'm just now stuck because I just got one root. I don't know what to do. So what we say is I'm going to hypothesize that this y is going to be the original root, which is e to the or original solution, multiplied by some function which is a function of t. I don't know what that function is, but I'm going to figure out what that function is. So that's the basic concept. Alright, so y is e to the power of r1t vt, and our original equation is y double prime plus a1 y prime plus a naught y is equal to 0. Okay. So we go ahead and get these numbers. So y prime becomes equal to e to the power of rt vt plus v prime plus r e to the rt v, that's my y prime, and then y double prime is going to be e to the rt v double prime plus v prime r e to the rt plus r v prime e to the rt plus v r e to the rt. Okay. So all that we have done is to do some amount of algebra, and we have just hypothesized that this is the solution, of course, provided I will be able to evaluate what this guy is. Okay, so that's a hypothesis that is being made. So y is going to be equal to e to the power rt and multiplied by something else, and we claim that this is a solution. This is the second solution. The second solution. The first solution is already e to the rt. The second solution is e to the rt multiplied by some function which I as yet don't know, but I would like to figure out what that is. And you can do the algebra. So y prime is this, y double prime is this. So multiply this guy with a1, and then y is, there's a c hanging in here everywhere, is c e to the rt times v, and you go ahead and add up all these guys. Okay. So the algebra you can do, I'm not going to do it, but this is what it is, and you are just going to add up all these guys, and you are going to get v double prime, which is that first term that you see there, and then twice r1 plus a1 times v prime plus r square plus a1 r1 plus a naught v equal to 0. Okay. So just add these guys up and clean it up maybe a little bit, and you should end up with this. Okay. Now what is this term here? Twice r plus a1 is equal to how much? Twice r plus a1 is what? This is my solution. Okay. So what is twice r plus a1? What are we looking at in here? The roots are equal, right? If the roots are equal, what is happening? This term is gone, right? Which means that the root is minus a1 by 2. So if the root is minus a1 by 2, what is 2 times the root plus a1? 0. Right? So this term is gone by virtue of the fact that the roots are equal. Okay, so the first term is gone. What about this term here? What about that term? That term is also 0, right? By virtue of the fact that this is a root to that, because this is what you are going to be ending up with if you say that that's my root. Right? So that term is also gone, right? So this was a very smart thing which some mathematician came up with. So because of the fact that these are equal roots, this is 0. This is 0 by virtue of the fact that this is the root of the equation itself. Okay, so this guy is gone and this guy is gone. So now you have a happy situation where you get v double prime is equal to 0. So what did we start with? We started with a hypothesis which said that y is going to be equal to the second root and that should satisfy the equation. So e to the power of rt, this r we already had established, times avt, and the v I did not know what it was, and then I plugged it in, and once you did a little bit of algebra, what you ended up with was v double prime equal to 0. And what does v double prime equal to 0 mean? What is v? Can I get the v? This means d2y, d2v, dt square equal to 0. Just brute force integrate it, right? So you are going to get v equal to some at plus b. So v is equal to c plus dt. Okay, dc plus d times t. Okay, and now we just say that there is no loss of generality in taking this as equal to 0 to start with, and therefore we say that the root is going to be e to the power of r1t times t. Okay, and on your home assignment I will just say that don't take c equal to 0 and show that you will get it, and you will get it. Okay, it's not a big deal. Okay, so y is going to be, the second root is going to be e to the power of r1t times t, and therefore the final solution is y is equal to c1 e to the power of r1t, which was the first solution anyway, plus c2t e to the power of r1t. Okay, so that's my final solution. Okay. Yeah.
Just one question that when the roots were imaginary, we were looking for two solutions so that at the end we can eliminate the iota terms of
Correct.
right? But here
I mean, that's the way I look at it, correct? You can look at it in various fashions. What we said was that because this is coming as the solution to a real system, I would like to somehow say that if my solution is also some kind of a real solution, it's something that's desirable. Otherwise, like what you were saying, you can use a plus ib and then push it together and then maybe do a manipulation and get rid of the I. Yeah.
So in this case, when the roots are equal, so I know that if roots are equal, my iota term is going to 0, right? Because if those roots were not equal, then I should get
no, there is no I term here at all.
Yeah. So why
there is no
even looking for the second solution?
Right. Why am I looking for it's a second order differential equation, so I need two solutions. Right? One solution is not enough. There are two conditions, right? Y and y prime at 0. So unless I have got two solutions, I can't get the proper solution to the equation. Right? So a first order differential equation, you will write the equation and you will have one condition. A second order equation, you will write the equation and you will have two conditions. Okay, the conditions could be, if we are saying that in some sense time is really time, then y at time t equal to 0 and y prime at time t equal to 0 will be given to us. Okay, but if I am talking about a second order equation, and if I am saying that t is not time but it is some kind of space, then you can have y at x equal to 0 and y equal to some other location. So some two conditions have to be given to me so that I can nail down the final solution. Okay. Okay, anything else? All right. Okay, so what we are saying is that if we are having a second order equation, we are getting a quadratic, and this quadratic I can solve, and you can get roots which could be either real roots, in which case there is nothing need to be done. The roots could be imaginary, in which case you can still do nothing, or you can say that I want a better solution, or I want a more physically palatable solution, if you will, and then convert it into sines and cosines. And if the roots are equal, then you can say that I'm going to have the solution which looks like a, the root itself, plus the independent variable times the root itself. So that's what the solutions are all about. Okay. So we look at a couple of examples. And your next assignment is going to be one where you have second order equations and you are going to work these guys out. And I'm okay with you using online tools, but I would like to also emphasize that it's always a good idea for you to go ahead and at least one or two of these, do them from the basics, because just by doing clicking and getting the solutions is always not going to be desirable. You do get into trouble when you do that. Okay, so this is an example: y double prime minus twice y prime minus 8y equal to some RHS. We have not at the moment taken any RHS, so we will not worry about the right hand side. So you go ahead and say y is equal to, for some reason I am going from r to lambda. So y is equal to e to the power of lambda t or lambda x, whatever, c e to the, and then you plug this in, you get that as the characteristic equation, and you get the solution to that. Okay, let's just do this one. So y double prime minus twice y prime minus 8y is equal to 0. This is the homogeneous part. We are only looking at the homogeneous solution as of now. So this is the homogeneous part, and if I want this, I'm going to use this, and I'm going to get lambda square minus twice lambda minus 8 equal to 0, and you can factorize this guy, lambda minus 4 lambda plus 2 equal to 0, and you get lambda equal to either plus 4 or minus 2. So the solution becomes y equal to c1 e to the power of 4t plus c2 e to the power of minus 2t. Okay, so that's the solution. Okay, x and t, that doesn't matter, so we'll just, to be consistent with that, this is x. Okay, all right, e to the power of lambda x. Okay. All right, next example, same thing, except that there is a small variation, and if you now go ahead and see, you are getting imaginary roots with the I in there, and if I just go ahead and say that I have done the algebra and my solution is y is equal to 1/2 plus minus root 3 by 2i, this is the solution that I get. So the final solution that I would have is c e to the power of 1/2 t. Remember, we said this was m plus in, and then cos root 3 by 2t plus sine root 3 by 2t. Okay. So this is when you are having imaginary roots. Okay. And last example, which is now if you have got a right hand side, the characteristic equation, and you need two conditions. At the moment we are not looking at the conditions, but once we get there we are going to be putting the conditions also. So it's a second order equation, y1 is given and y prime at 1 is given. So that completes the specification of the question itself. Okay. So you've got the homogeneous part as y equal to c e to the 3x plus another constant c x e to the power of 3x. So this is what we had shown a little while ago. That is, you take the original solution, just multiply it by the independent variable. Okay. All right, so fairly straightforward stuff. Now we are saying that we are getting two solutions, right? But the solutions have to be independent. How do I check that they are independent? Okay. Once again, we are going to just show this without proof. There is something called a Wronskian, and you can evaluate the Wronskian, which is the determinant of y1, y2, y1 prime, y2 prime. Okay, so this is the Wronskian, and if the Wronskian is not equal to 0, then y1 and y2 are independent. We are not proving this, we are just taking this. Okay. So you take the Wronskian, which is f1, if there are 3 functions, then you can take the 3. At the moment we have only 2. You have got a y1, you have got a y2, y1 prime and y2 prime. Okay. So if you are finding that this is not equal to 0, then y1 and y2 are independent solutions to the situation. Okay. If it is equal to 0, does not make them dependent, you have to do something else to figure out whether they are independent or not. Okay. So as of now, we are not going to get into that. All that we are saying is, if you have got two solutions, if you want to figure out whether they are independent or not, go ahead and compute the Wronskian. Now let's go ahead and look at something called the Abel's theorem. Okay. All right. So this is something that we are going to be finding useful sometime later. But since we are talking about the Wronskian, it might as well we might as well go ahead and see what this is. Okay. So we have said that there is something called a Wronskian, and the Wronskian is y1, this is w, is the determinant y1, y2, y1 prime, y2 prime. What is y1 prime and y2 prime? What is y1 prime? I just said this is it, this is not 0, determinant, nobody bothered. What is y1 prime? It's the derivative of y, that's all it is. Okay. y1 prime is the derivative of y1, y2 prime is the derivative of y2. Okay, so that's the Wronskian. Okay. All right. So the Abel's theorem, again, these are mathematicians who have a lot of insight. So what the theorem says is that the Wronskian, if I have the governing equation as y double prime, so we just are going to be interchanging with d2y, dt square and y double prime. So y double prime plus a1y plus a naught is equal to 0. Okay. We're talking about a homogeneous equation as of now. If I have got a differential equation like this, then the Wronskian is going to w prime plus a1w is equal to 0. The Wronskian satisfies this. Okay, so this was the theorem. Okay. We are not going to prove it, we are going to just demonstrate it and nothing else. Okay. So we have just seen what the Wronskian is, y1, y2, y1 prime, y2 prime, that's the Wronskian. And what is w prime therefore? The derivative of the Wronskian, that's all. Okay. Y prime is the derivative of y, w prime is the derivative of the Wronskian. Okay. Okay. So what is w prime therefore? What is w? Can you help me with what is w? Determinant, what is that determinant? y1, y1, y2 prime minus y2, y1 prime. Okay, so that's the Wronskian. Okay, so the derivative of the Wronskian, w prime, okay, is going to be y1, y2 double prime plus y2 prime, y1 prime minus y2, y1 double prime plus y2 prime, y1 prime. Okay. So that's the derivative of my Wronskian. So the Wronskian derivative, this guy goes away, right? So you've got y1, y2 double prime, y1, y2 double prime minus y2, y1 double prime. Okay, now suppose, now this Wronskian, what is y1 and y2? What is y1 and y2? The solutions to the original differential equation. Okay, okay. Now, if they are the solutions, I can write this as y2, y1 also, right? No problem, right? So what's going to happen to this guy here? Will this guy remain the same? There will be a negative sign outside it, okay, but that's not going to bother us, okay. So we'll just say that we have y1, y2, y1 prime, y2 prime, and once you have defined the Wronskian in that particular fashion, you be consistent and move ahead, that's all. And then the theorem will come about, and if you are going to flip these, there's going to be no loss of generality, okay, that you can see yourself. By the way, I had asked that in an exam last time and more than half of them did not get it proper. Okay. Okay. So there's no problem in just flipping these two. You'll just end up with a negative sign and the end result is going to remain the same. Okay. All right. So w prime, which is the derivative of the Wronskian, is going to be this guy here. Okay. So y1, y2 double prime. So now the Abel's theorem, it said that the Wronskian is going to satisfy this equation here. Okay. So we'll just plug the numbers in and see if it's going to satisfy. That's all we are going to be doing. Okay. We already have w prime. So w prime is y1, y2 double prime minus y2, y1 double prime, and then plus a1, and then the Wronskian already I have, which is y1, y2 prime minus y2, y1 prime is equal to 0. Okay. So you just group the terms together, the algebra is all there, you just group the terms together, take the y1 common, y1 when you take it common, you're going to get y1 and then y2. So y1, y2 double prime plus a1, y2 prime. What is that? Right. So minus a naught y. Okay, because the original equation was dy double prime plus a1 y prime plus a naught y equal to 0. This is what is the base equation that we are working with. Okay, and y1 times, now what you got was y2 double prime plus a1 y2 prime. Remember, y is just the generic variable, the solution. Okay, we'll stop here for today. I'll see you again tomorrow at 11:30. Thank you very much.